Welcome everybody to this new webinar about the EVEREST project. This webinar is part of a series of webinars that you can find on YouTube or linked within the main EVEREST webpage. This webinar is organized around the runtime components of the EVEREST System Development Kit. I'm Gianluca Palermo, full professor at Politecnico di Milano and member of the EVEREST team. I will provide you a few words to introduce and conclude the webinar, including a final demo. But then, other technical content on the specific components will be provided by other EVEREST researchers from three main partners, in particular Paolino, Virtual Open Systems, and IT for Innovation. EVEREST is an European project started at the end of 2020, which aims at simplifying the development of complex big data applications for FPGA-based data centers. The focus of the project is on the EVEREST System Development Kit, the SDK, which is a compilation and runtime framework for optimizing the deployment of application workflow on heterogeneous, reconfigurable, distributed, and secure large-scale systems. The development of the EVEREST SDK has been driven by three main use cases: an application for prediction of renewable energy, an application for high-quality monitoring, and a traffic modeling and prediction system. These applications have been identified as representative of a large class of applications that we want to be able to support with the EVEREST SDK. The structure of the webinar will be the following. First, Michele Paolino from Virtual Open System will introduce the EVEREST runtime part of the SDK. Then, we will go through the three main components of the EVEREST runtime, and in particular, EVKit, that will be presented by Jakub Beranek from IT for Innovation, the Margo framework from Roberto, Rocco, Politecnico di Milano, and finally, the virtualization extension from Samuele, Paone, Virtual Open System. We will not only introduce the components, but we are going to show you also some demos about their usage.
Hello everybody, this is Michele Paolino from Virtual Open Systems. I am the Work Package 5 leader, which is the place where the components described in this webinar were designed and developed. The EVEREST runtime is a distributed and virtualized environment based on the KVM hypervisor, on the open source KVM hypervisor that supports the selection of accelerator variants that are coming from the EVEREST SDK. So in practice, the EVEREST SDK produces variants that are then given as an input to the runtime environment. The runtime environment then runs them in a virtualized, distributed, and auto-tuned way. But how does this happen? Actually, this happens thanks to three main components that I'm going to describe here briefly and that then will be later described in more details. The first one is EVEKit, who is a distributed runtime library developed within the EVEREST projects that distributes and load balances workloads supporting both CPU and FPGAs. The second one is called Margot, and actually it provides dynamic adaptation and auto-tuning by choosing the best runtime configuration according to hardware status or availability and input features. The last one, the third one, is called EVEREST SRIOV FPGA Manager. We call it ESFM. Is the virtualization support layer, meaning an FPGA virtualization solution designed and developed during EVEREST that uses SRIOV to enable direct communication between the VMs, the virtual machines, and the FPGA kernels. It is able to attach and detach accelerator in a flexible way, as you're going to see in later in this webinar. So next, we're going to describe each one of these components, one after the other, in more details.
The first component of the EVEREST runtime system is called FKit. It is a distributed runtime whose main goal is to allow simple distribution and load balancing of embarrassingly parallel computations onto a set of workers. These workers can either run on the same node, or they can run on multiple nodes within the same distributed cluster. FKit supports execution of kernels that run either on the CPU or on an attached FPGA device. FKit can also cooperate with other components of the EVEREST runtime system. It can cooperate with Margot to choose the best CPU or FPGA kernel variant based on the current load, and it also has two modes of using FPGAs. It can either use them through the virtualization extensions, where it is able to execute kernels on FPGAs running inside virtual machines, or it can use another software developed within the EVEREST project called Olympus, which allows it to run kernels directly on FPGA hardware without any virtualization. FKit provides a simple API for clients, which can be used to compute kernels on remote workers and thus distribute and parallelize their computation. This API is currently available in Python and Rust. However, it is easy to add support for new languages. Internally, FKit is implemented in Rust, which handles the network communication and distribution using the 0MQ message broker. FKit also uses a thin C++ layer, which manages the communication with the FPGA and deserialization of network requests. To communicate with the FPGA, the C++ layer uses either Olympus or the virtualization extensions, and it is also integrated with auto-tuning and variant selection using the Margot component. Here we can see how the traffic simulator use case uses FKit to parallelize some of its kernels. Since the simulator is written in Python, it uses the Python FKit API. On a high level, FKit offers two kinds of computations. The first one is the offload of a kernel, which can be sent to a remote FKit worker, which computes it and returns back the response. Here it is used by the traffic simulator to distribute and parallelize the computation of alternative routes for individual vehicles. The second kind of computation offered by FKit is a broadcast message. This can be used to send the same message to all connected FKit workers, which can be used, for example, to synchronize shared state amongst all the workers. In this case, in the traffic simulator, it is used to update a map, which is... Here we will see a demo of how the traffic simulator can be used together with FKit to parallelize and distribute the computation of the PTDR kernel. In this setup, the traffic simulator runs on a CPU, and an FKit worker is deployed on a node with an attached FPGA. While the simulator is running, it communicates with the FKit worker through TCP/IP, and it offloads the computation of the PTDR kernel to it, which is then executed on an FPGA, and the result is returned back to the simulator. Hi. In this demo, we will take a look at how we can use this distributed runtime FKit in order to distribute the computation of PTDR kernels from the traffic simulator and to help us execute them on an FPGA. So this demo will show two components, the traffic simulator and the FKit runtime. And first, I will show how to configure the FKit runtime. So to do that, we will need to clone it from the EVEREST Git repositories, and since it uses Git submodules, we will need to use the recursive flag so that it downloads all the nested directories, otherwise some source files will be missing. once it's downloaded, we can go to the fkit directory, and the fkit runtime is written in Rust. So as a prerequisite, you need to have a Rust toolchain installed. Any recent Rust toolchain should be good for compiling fkit. And if we have the toolchain installed, we will have the cargo binary available, so we can execute cargo run. We want to compile and run fkit with optimization, so we will use the release flag. And we also want to enable the ptdr feature, which is done using this flag. And at the beginning, let's just see what are the available command line flags. So when I execute this command, in the first time, cargo will compile the whole project, the fkit worker. In the following runs, everything will be already compiled, so we just need to run the command and it will be executed immediately. Now we have to wait a little bit until the project is compiled. Okay, now the compilation was finished, and we can see the command line parameters that we need to provide to fkit to run ptdr. So we need to provide some input data, the ptdr profiles, and if we want to run on an FPGA, we also need to provide a ptdr bitstream, which is the ptdr kernel compiled for the FPGA. We will also need to provide two TCP IP addresses, which will serve for communication with the traffic simulator. The compute address is used for computational requests, where the simulator asks fkit to compute a kernel, and the management address is used for some internal bookkeeping and sharing some shared state. So, since I want to execute the fkit worker in FPGA, I will first need to load some FPGA state. So on this cluster, I have this bash script, which loads some shared environment variables that will enable me to use an FPGA. And once I have done that, I can execute or start the fkit worker and run it on an FPGA. So I need to provide parameters. So I will provide the path to the ptdr profiles, the FPGA bitstream, and the two addresses that will be used for communication with the traffic simulator. Now the worker has been initialized and it is currently loading the ptdr profiles from this input file. Now the profiles have been loaded and the fkit worker is now waiting for requests from the traffic simulator, and for each request it will compute the ptdr kernel. We could start multiple such workers on different nodes. Some of them could run on the CPU, some of them could run on an FPGA, and all of them will contribute together to speed up ptdr computations in the simulator. Okay, so now let's go set up the simulator itself. We will again need to clone it, this time from a different repository. And the simulator is a Python project, so we will need to create a Python virtual environment, and we will need to use at least Python 3.7. So I will create a virtual environment, install some initial dependencies which are needed, and after that I can install the project itself. This will download all the dependencies of the traffic simulator, which are many Python libraries and packages used by its implementation. Okay, so the traffic simulator's dependencies have been installed. And now if I want to execute the traffic simulator, it is done through this configuration file, which can be used to configure various parameters of the simulator, like the departure time of the cars, or how often will the map be updated, and so on. And most importantly, we select the input map, which decides which vehicles will be simulated in the simulator. And we can also choose the implementation of PTDR, which is decided by this route selection field. So this default uses just a Python implementation, but if we set it to the value distributed, we will actually redirect the traffic simulator to fkit, and it will start communicating with fkit over TCP/IP using those provided addresses, and these ports are used by the simulator by default, so that's why I have chosen them in fkit. Okay, so I will now modify the config file to redirect the simulator to fkit, and also to use a different vehicle input file, which corresponds to the PTDR profiles that I have used for the fkit worker. So this is the file with the vehicles that we will use as the input for the config file. So I will change it here in the vehicle's path. And I will also change this route selection field to distributed, which will cause the simulator to communicate with the fkit worker. And now it should be possible to run the simulator, tell it the configuration file that we want to use, and start it. So at the beginning, the simulator will download some map files, and then it will start the simulation. So here on the left side, we can see the individual steps of the simulation that are being printed. And on the right side, we can see that the fkit worker is executing the PTDR kernels requested by the simulator on an FPGA. And that's the end of the demo.
Hello, I'm Roberto Rocco, and I present you the Margot Auto-Tuning Framework, which provides the application with dynamic adaptation functionalities. Its use ensures that the application can select the best parameterization, that is, the best values for its knobs, given the optimization problem and the features of the input and the execution environment. Margot operates over a map case cycle. It checks the application behavior through monitors and metrics, analyzes the data, plans an eventual change, and enacts it through knob changes. The Margot Auto-Tuning Framework is not monolithic, but includes modules to attach upon need. The auto-tuner interacts with the application following the knowledge, which can come from static profiling performed previously or by dynamic learning. The Agora component enables knowledge learning by driving a configuration space exploration and modeling the response of the system to the knob choices. Agora produces knowledge that reflects the system's current behavior, but does not guarantee that it will stay up to date for the entire execution. A dynamic execution scenario may cause the application to wander into cases not planned by the Agora component. The tail runtime observer ensures that the framework can handle such cases, observing the behavior of the application and triggering the restart of the learning procedure if the knowledge does not reflect the status of the execution. Alongside these two components, the Margot Auto-Tuning Framework also contains two modules able to split the bond between the autotuner and the application. Using Adam and Brian, the user can execute the best configuration choice on a different execution environment, also enabling optimization of applications written in languages other than C++. To leverage the possibilities of the Margot Auto-Tuning Framework, the user must adapt its code to introduce the added functionalities. The process is relatively straightforward, as shown in the code snippet on the right. The changes follow the flow of the application, setting the value for the knobs and using them in a monitored block. Alongside code changes, the user must provide a configuration file describing knobs, metrics, input features, and the optimization problem. The configuration file also contains information about the interconnection with the Agora and Theo components. Given the configuration file, the user should compile its application linking to Markov, and the compiler will generate the interface starting from the configuration file. The output of the compilation process is an executable bundled with the knob optimization mechanism. In this simple demo, we show the behavior of an application leveraging Markov functionalities. The application executes one of two variants of a kernel. One is one serial and one leveraging OpenMP and thus being parallel. The application fetches the number of available threads and chooses the burst variant accordingly. As you can see in the demo, the application doesn't get many changes from introducing Markov functionalities, and now we can proceed with the execution. In the terminal on the right, we start the execution of the Agora component through a Docker container. The terminal on the left, on the other side, we will compile the application and we will run it, linking to the MQTT message broker and thus to the Agora component. We expect the execution to go through a first phase with many iterations and through a learning procedure. So we're building the knowledge of the application with the Agora component, but at a certain point we can see that the values we are seeing get to a point right here in which we have the timing value which is set. So the application has the knowledge about the execution, and so it chooses the OpenMP variant because it features, it fetches that there are 12 threads present. So the execution from now on continues optimally.
Hello, I'm Samuele from Virtual Open Systems, and now I'm going to present an overview of the EVEREST virtualization extension for PCIe devices. To support virtualization in PCIe-based FPGA, VOS developed the EVEREST SRIOV FPGA Manager, ESFM. Its main features are initialize the PCI device and flash the bitstream, create the SRIOV virtual functions, which act like a device and are seen as such by the virtual machines. It allows the users to attach or detach virtual functions from the virtual machines and use them concurrently. Moreover, ESFM can reconfigure the overall number of virtual functions available to the system. The main ESFM components are three. ESFM, which is a bash script that acts as a user program interface. It initializes the system to create the virtual functions and attach them to virtual machines through a technology called device pass-through. It can reconfigure the virtual functions number and eventually flash a new bitstream. Then there is the QDMA manager, which is a utility program used by ESFM to take care of the pass-through and SRIOV requirements. In the end, there is program Vivado and program XSCT, which are TCL scripts used by ESFM to flash the bitstream. With this setup, the EVEREST virtualization runtime enables a direct and high-performance connection between a virtual function and a virtual machine, in a way that multiple pieces of the FPGA are used by multiple virtual machines. This can drastically improve resource utilization, especially considering dynamically virtual function attach-detach strategies that enable a virtual function to be assigned to a virtual machine only when effectively needed. More information and an additional demo are available at the link above, where it is possible to find a specific webinar produced by Virtual Open Systems showing the virtualization extension feature on an SOC-based FPGA.
We are going to see now a node level demo of the EVEREST runtime. Before starting it, let me introduce it. The image on the right represents a simple backbone of the three scenarios. We have two virtual machines running on a single host, including the EVEREST virtualization extension, and an hardware function on an FPGA that is attached to one of the virtual machines or to another one, depending to the virtual manager decision. Within the virtual machines, there are the application running using the Margot library. The demo will be divided in three parts. The first one is a static one, where we'll show only how, thanks to the EVEREST runtime, the application becomes agnostic to the presence or not of the hardware function, and two dynamic ones, where the hardware function is dynamically detached or attached from one virtual machine to another one. In the first static scenario, we consider the case of a pre-allocation of the hardware function to one of the virtual machines. In this scenario, the EVEREST runtime supports the application by making it agnostic from the resources that are attached to the guest virtual machine. The presence or absence of the hardware function attached is detected by using an ESFM file within the guest virtual machine by Margot. To simplify the video and the demo, instead of running two virtual machines, we will launch 2 times the same application instance before and after attaching the hardware function to the virtual machine. In this part of the demo, we have 3 terminals. The one on the right is on the guest machine and is where the application is running. The 2 on the left are on the host machine. On top left, we will use the terminal to attach or to detach the hardware function from the virtual machine, mimicking the actions of the virtual machine manager, while on the bottom left there is the status of the attached hardware function to the guest virtual machine. We start with a virtual machine without any hardware function attached, and we launch our application that detects that there is no hardware function available and then runs on the version 0, that is the pure software version. Then we stop the execution of the application, and on the host terminal we attach the hardware function to the virtual machine. This becomes also visible on the bottom terminal, where the presence of an attached hardware function is now highlighted by a new entry. We restart the application, and without any modification to it, and thanks to Margot, the presence of the hardware function is then detected, and the version executed becomes the one using the FPGA acceleration, which is the version 1. Now, in the second part of the demo, we are going to see a scenario in which the reconfiguration of the hardware function happens during the application execution. The joint Margot ESFM support permits to have it transparently. An example is the case in which an application is running on a virtual machine with an attached hardware function, and then a new virtual machine, maybe with a higher priority, is also allocated on the same physical machine. As a consequence, the virtual machine manager decides to remove the hardware function to the previous virtual machine, the blue one in the image, that is still running, and attach to the new virtual machine. This scenario demonstrates how the flexibility introduced by the EVEREST runtime enabled the infrastructure with a better management of the FPGA resources. For this second part of the demo, we have the same terminals as before. The guest terminal on the right and the 2 host terminal on the left. As usual, we start launching the application without any hardware function attached. The application then detects that there is no FPGA acceleration available and runs the pure software version. After a while, at this time without stopping the application, we dynamically attach and remove the hardware function from the virtual machine, mimicking the absence or presence of a competing higher priority virtual machine on the same physical server. We attached, and now we detach. The hardware function for the virtual machine, and now we see that the FPGA is detected that the acceleration is not more present and the version 0 is run. In the third and last part of the demo, we enhance the previous scenario by also providing an application level feedback to the virtual machine manager. This feedback is called happiness in the Margot jargon. Let's start with a situation in which two virtual machines are allocated on the same physical machine. The hardware function is attached to the blue virtual machine. When the application execution starts, the application in the blue virtual machine detects the presence of the hardware function and provides an happiness value that reflects a possible hardware function removal by the virtual machine manager. Identically, the same happens to the green virtual machine, where the happiness value is instead related to the possibility of having a hardware function attached. The virtual machine manager, knowing the happiness value for all the running application, solves a simple optimization problem and decide if there is the need of reconfiguring where the hardware function is attached. So, if moving the hardware function for the virtual machine blue to the virtual machine green. In this example, the virtual machine manager decided to detach the hardware function from the blue one and to attach to the green one. The happiness value are also modified from the application to reflect this actual change. Of course, possible changes in the execution environment or data-aware processing can dynamically modify the application happiness value. In this example, the happiness value notified from the application running on the blue virtual machine increased a lot, meaning that there is a strong request in using the FPGA acceleration. The virtual machine manager then changes again the hardware function allocation to reflect the happiness value. Let's see the actual demo. As usual, we run the demo using a single virtual machine. This time we have 4 terminals, 3 on the host and 1 on the guest. The only one on the guest is on the top right corner, where there is the application running. As usual, on top left we see some command that mimics the virtual machine manager actions. On the bottom left it is shown when the hardware function is attached to the virtual machine. And on the bottom right, we will see the happiness values provided by the application and received on the host side. As usual, we start our application. Then we will see that the happiness value is immediately received by the host, communicating the happiness in having an hardware function, if available. Now, on the top left corner, we satisfy the request by attaching the hardware function, and after a while, the application recognizes it. The application also switches the execution to the hardware function version and changes also the happiness value. Of course, the opposite happens when the new hardware function is detached. To conclude this webinar, I want only to remind that this webinar provided an overview of the EVEREST runtime as part of the EVEREST System Development Kit. The webinar is part of the dissemination and communication effort of the project. More information about the project and on the other webinars of the EVEREST series can be found on the project webpage www.everesth2020.eu. Thank you for your attention.